Section: Introduction. In this section, we explore the growing interest in applying advancements in generative AI and large language models, LLMs, to tackle significant decision-making challenges. Initial efforts have shown promising results in both virtual and real-world settings, but we still face considerable obstacles. Besides the need for generalization in supervised learning, effective decision-making under uncertainty requires us to balance two key abilities: exploitation, which is about making the best choice based on current information, and exploration, which involves trying new options for future benefits. This balance has been widely discussed in literature. Recent studies have examined how well LLMs can manage this exploration-exploitation balance by using in-context prompts that include problem descriptions and historical data. While these studies focused on simple reinforcement learning tasks, the outcomes have been mixed. They indicate that LLMs struggle to perform these tasks without additional guidance, although they can improve with specific prompts or fine-tuning on relevant data. However, these solutions often do not apply well to more complex scenarios, as many decision-making tasks lack concise summary statistics, and fine-tuning can be costly or data-limited. Driven by these insights, we investigate how models like GPT-4 and GPT-3.5 can explore and exploit within specific contexts, aiming to utilize a pre-trained LLM as part of a broader decision-making system. We concentrate on contextual bandits, which serve as a standard model for the explore-exploit dilemma. In our exploitation evaluations, we task the LLM with determining the best action based on a history of context, action, and reward data. Our findings reveal that while LLMs can effectively exploit in smaller problems, their performance declines as the problem size increases. We also discovered that in-context summary techniques can enhance performance, yet LLMs still fall short compared to a basic linear regression model. For our exploration evaluations, we assess LLMs as oracles that suggest potential actions from a vast action space. We introduce a text-based multi-armed bandit task where actions are free text responses to open-ended questions, and rewards are based on how close these responses are to a chosen answer in an embedding space. Given the complexity of the action space, traditional bandit methods are not suitable. Instead, we find that LLMs can generate a small set of candidate actions that can be used with standard bandit algorithms. We test various prompting strategies and find that they yield good exploration results. We also replicate our experiments on a larger bandit task using paper titles and abstracts from arXiv, leading to similar conclusions. Our results contribute to a rapidly expanding body of work that examines the use of pre-trained LLMs for in-context reinforcement learning. Previous studies have shown that LLMs struggle with multi-armed bandit and contextual bandit tasks, with positive results limited to very simple scenarios or requiring significant adjustments. Some research has focused on using LLMs for dueling bandit tasks and learning in games. While our work primarily assesses LLMs as algorithms, other studies have explored whether LLMs display human-like biases in decision-making. The broader literature on in-context learning aims to solve various tasks by providing all necessary information in the LLM prompt, and our exploitation experiments relate to the selection of examples for in-context learning. We also draw inspiration from research that uses LLMs as action priors within larger reinforcement learning frameworks. Much of this work follows a proposer-verifier model, where an LLM suggests sequences for a verifier to evaluate. In contrast, our goal is to systematically assess LLM's abilities to explore large action spaces independently from other decision-making components. Lastly, there is parallel research focused on training transformers from scratch to address various reinforcement learning tasks. In summary, we examine multi-armed bandits and contextual bandits, which are well-established frameworks for understanding the explore-exploit trade-off. In multi-armed bandits, we have a set number of rounds and options, where the learner selects an action and receives a reward from an unknown distribution. In contextual bandits, the learner also considers context before each round, with the expected reward depending on both the context and the chosen action. The learner's objective is to maximize cumulative rewards by balancing exploration and exploitation. An exploitation oracle can enhance standard bandit algorithms, while an exploration oracle can help identify candidate actions to streamline the decision-making process. Section Summary. In this section, we explore the application of large language models, LLMs, in decision-making tasks, specifically focusing on their ability to balance exploration and exploitation in contextual bandits. Our findings indicate that while LLMs can effectively exploit in small problems, their performance declines in larger contexts, and although they show promise in generating candidate actions for exploration, they still underperform compared to traditional methods. Section: LLMs as exploitation oracles. In this section, we evaluate how well large language models, LLMs, can exploit decision-making tasks that involve uncertainty in outcomes. We present LLMs with tasks inspired by multi-armed bandits, MAB, and contextual bandits, CB. In a CB task, the LLM receives a history of context arm reward combinations and must select the best arm based on this history in the current context. In contrast, a MAB task does not include context. We create these tasks from specific distributions known as exploit puzzles and visualize the results by plotting the proportion of correct answers against task difficulty. For our MAB experiments using GPT-4 and GPT-3.5, we explore why these models struggle with MAB tasks when given raw history. We test two types of prompts, one where arms represent different colored buttons and another where they represent various advertisements. The LLM is tasked with choosing the arm that yields the highest reward. We also implement chain of thought, COT, prompts, resulting in 4 prompt designs. We define an MAB exploit puzzle based on a gap parameter and history size. Each task has 5 arms, and we randomly select one arm to have a higher expected reward. We generate a history of rewards for each arm over a set number of rounds, where the rewards are random draws based on the expected values. We create multiple tasks for different gap values and measure difficulty by calculating the empirical gap, which is the difference between the highest and second highest average rewards. We assess the LLM's performance by determining the fraction of tasks where it selects the arm with the highest reward. Our findings show that both GPT-4 and GPT-3.5 perform poorly on these MAB puzzles, especially as the history length increases and the empirical gap decreases. While GPT-4 generally outperforms GPT-3.5, using COT reasoning slightly helps GPT-3.5 but negatively impacts GPT-4. Performance remains consistent across our prompt designs. In the case of CB puzzles, summarizing history can be challenging. We focus on a linear CB model where the expected reward is a linear function of the context. We create tasks by sampling parameters for each arm and generating a history of rewards based on these parameters. The LLM is then asked to choose the best action based on a new context. We present these tasks using a modified prompt that does not reveal the linear nature of the model. We define a correct answer as the arm that maximizes expected reward for the new context. We measure the fraction of correct answers and analyze how this varies with the effective gap, which indicates task difficulty. Our results indicate that GPT-4 performs nearly perfectly on smaller puzzles but struggles as the problem size increases. To address this, we implement several strategies inspired by existing literature to improve performance. These include selecting the closest contexts to the new context, clustering contexts, and combining these methods. We present the results without disclosing the mitigation strategies used. Our experiments show that these mitigations can improve performance, achieving around 80 to 90% accuracy without COT prompting, although this drops when COT is used. While these strategies help manage larger histories, current LLMs still face challenges with moderately sized problems. We visualize the performance of GPT-4 with mitigations and find that while our methods outperform unmitigated models, they still fall short of the performance of a linear regression baseline. Section Summary. In this section, we evaluate the performance of LLMs on decision-making tasks inspired by multi-armed bandits, finding that both GPT-4 and GPT-3.5 struggle with these tasks, particularly as history length increases and empirical gap decreases. We also explore mitigations for contextual bandit tasks, demonstrating that while our strategies improve performance, LLMs still fall short compared to linear regression baselines. Section: CB Exploit Puzzles, Text-Based. In this section, we conduct a robustness check by repeating our experiments on a text-based exploit puzzle. In this puzzle, the contexts are items found in a room, such as animals or objects on a table, and the actions we can take have specific meanings, like eating a food item or leaving the room. The rewards we receive are numerical and depend non-linearly on both the context and the action taken. For more details on our experimental setup, we refer to the CSEC exploit_app. Our results, shown in Fig. Words, indicate that while the reward function is nonlinear and a linear baseline achieves only 70% accuracy, all configurations still perform significantly worse than this linear baseline. Next, we explore the capability of pre-trained large language models, LLMs, to navigate large action spaces. We utilize the inherent biases of an LLM to generate a small set of potential actions from a text-based action space, which we then analyze using a standard multi-armed bandit (MAB) algorithm. We focus on two exploration tasks: answering open-ended philosophical questions and suggesting titles for archive research papers based on their abstracts. Each specific workload within these tasks is termed an explore puzzle. For the QA task, we define the best arm as a contrarian answer produced by another LLM, while for the archive task, it is the actual title of the research paper. The expected reward for an action is determined by the similarity between this action and the best arm in the embedding space, which we calculate using the sentence BERT model. The actual reward we observe in each round is a random sample based on this expected value. Given the vast action spaces for these tasks, traditional bandit algorithms that randomly sample actions tend to fail dramatically. If the algorithm were aware of the embedding space and the relationships within it, it could theoretically use advanced techniques to focus on better performing areas over time. However, these methods are not practical in high-dimensional spaces like ours due to their exponential complexity. For the explore puzzle involving open-ended questions, we use the LLM to create a dataset of 10 questions, each with several reasonable answers and one intentionally contrarian answer. For instance, one question was, what does it mean to live a fulfilling life? With the contrarian answer being, fulfillment comes from embracing discomfort. Each question-answer pair forms a task for evaluation. We prompt the LLM to suggest a varying number of candidate answers and then apply a MAB algorithm over these candidates for a realistic time frame. We repeat this process multiple times for each task and calculate the average reward. We test different prompting strategies, including generating suggestions all at once or one by one, and whether to encourage diversity in the answers. We also compare these strategies against a baseline where candidates are chosen randomly. Our findings, illustrated in Fig. UCB, show that all prompting strategies yield similar average rewards, peaking around 3 or 4 suggestions, while the random baseline performs poorly. We conclude that the LLM effectively serves as an exploration oracle. Notably, the suggestions generated by the LLM are diverse and reasonable. For example, when asked about the role of technology in society, the first 5 suggestions included various perspectives, such as enhancing communication and driving innovation. Additionally, we confirm that the candidate suggestions are significantly different from each other, as shown in Fig. Hist, which visualizes the expected rewards across the candidate set. Overall, while detailed comparisons of prompting strategies may not yield significant insights due to the imprecision of sentence embeddings, our experiments demonstrate the LLM's potential in exploration tasks. Section Summary. In this section, we conduct robustness checks on our context-based (CB) experiments using a text-based exploit puzzle, finding that while our nonlinear reward function outperforms a linear baseline, all configurations still fall short of its performance. We also explore the effectiveness of pre-trained LLMs as exploration oracles in generating candidate actions for open-ended questions and archive paper titles, demonstrating that our LLM-generated suggestions significantly outperform a random selection baseline. Section: Explore Puzzle, Archive Abstracts and Titles. In this section, we conduct similar experiments using a larger dataset of paper titles and abstracts from archive.org. We gather 10 pairs of paper abstracts and titles from each of the 41 different archive categories, covering various academic fields, using the Archive API. To ensure that these papers are not part of the training data for GPT-4o, we only select papers uploaded after June 2024. Each abstract title pair represents a task, as previously mentioned. We evaluate GPT-4o as an exploration oracle for these tasks, similar to what we did in the earlier section. For each abstract, we prompt GPT-4o to create k alternative titles, which we then use in a bandit algorithm. We apply the same algorithm, UCB1, with a time horizon of 1000. We calculate the expected time averaged reward, which is the total reward divided by the time, and find the average reward for tasks within the same archive category. We experiment with both all at once and one by one prompting strategies and visualize our results, focusing on 6 archive categories. To evaluate the ability of the language model to specialize in a task, we compare it against a stronger baseline where the candidate titles are generated by GPT-4o using only the category information, not the abstract. We present results for other archive categories in a table, showing the average reward for different values of k and both prompting methods. In our findings, we conclude that both prompting strategies significantly outperform the baseline, and their performance generally improves as k increases.